At the dawn of the 20th century, the structure of the atom remained a mystery, but this was soon to change as in May 1911, having already won the Nobel Prize for his work on radioactive decay, Ernest Rutherford proposed a bold new atomic model, transforming our understanding of matter. At the time, Rutherford was Chair of Physics at Manchester University and deeply invested in understanding alpha particles, a type of radiation frequently emitted during radioactive decay. But his interest in alpha particles had started much earlier, during his days as one of J.J. Thomson's research students, here at the Cavendish Laboratory in the late 1890s. Within these walls, he had revealed that the newly discovered radioactive decay of uranium occurred due to not one, but two distinct types of radiation. Calling the less penetrating of these alpha radiation, he went on to spend the next 10 years tirelessly trying to understand its properties, students establishing himself as the leading authority on alpha particles. Once in Manchester, aspiring to make increasingly precise alpha particle measurements, Rutherford collaborated with Hans Geiger to develop two new methods of measuring single alpha particles, one of which would soon become the now familiar Geiger counter. However, issues with its operation due to alpha particle deflections of residual gas molecules in the counter meant Geiger was tasked with investigating atomic deflections of alpha particles further, a decision that would ultimately lead to Rutherford's atomic model. Geiger modified their counting experiment to the now famous gold foil experiment, where alpha particles were fired at an aluminium and later gold foil. Geiger had been carefully measuring the small forward angles through which most of the particles scattered, using a scintillator. But Rutherford's meticulous attention to detail meant he refused to neglect any angle of the experiment, no matter how unpromising, a decision that would prove crucial to their later discovery. Marsden, an undergraduate student at the time, was the perfect candidate to investigate whether any alpha particles were deflected through these unlikely large angles. Expecting to see nothing at all, they were all astonished when Marsden observed many tiny transient flashes of yellowish light on the screen. Summed up no better than by Rutherford himself, "It was quite the most remarkable event that had ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." But why was this result so remarkable? At the time, the best theory of atomic structure was J.J. Thomson's plum pudding model, proposed in 1904, where his negatively charged electrons were embedded in a diffuse uniform sphere of positive charge, just like plums in a plum pudding. But this diffuse sphere of positive charge would be far too insubstantial to deflect the fast-moving, massive alpha particles through such large angles. Spending 18 months puzzling over this huge inconsistency and instructing Marsden and Geiger to carry out further experimental tests, Rutherford concluded that the only way a collision could be so effective as to completely turn the alpha particle around was if all the positive charge of the atom was concentrated at a point. Deriving the now famous Rutherford scattering formula, based on electrostatic repulsion, he predicted the angular distributions of the scattered alpha particles, a prediction which explained the experimental results exceptionally well, even for large scatter. Using this to argue that the atoms were more like a solar system than Thomson's plum pudding model, he proposed his highly successful atomic model, in which most of the atom's mass is concentrated in a tiny positively charged nucleus, surrounded by orbiting electrons. Despite accurately predicting the scattering results, there were still many questions to be answered. The atomic model was highly unstable, as the moving charged electrons would radiate energy and spiral into the nucleus. But this problem was soon solved by Niels Bohr on applying quantum theory to the atom, which with later improvements remains valid to this day. But this wasn't all. Their experiment pioneered the use of particle scattering to investigate subatomic structures, a groundbreaking technique which became fundamental to everything from the particle physics experiments that followed to electron microscopy and far beyond. Building on his hugely successful work on alpha particles, but now as a tool to understand the atomic nucleus, Rutherford returned to Cambridge in 1919 as Cavendish Professor, ushering a transformative new era of nuclear physics. Under his leadership, researchers at the Cavendish achieved the extraordinary. The neutron was discovered, the atom split, antimatter production observed, and the first artificial nuclear fusion reaction created, all under his watchful eye. His remarkable sharp intuition, tireless energy, and imagination for profound yet simple experiments revolutionized atomic physics and inspired many generations of scientists to come.